This sort of explanation, it works for some people. Other people prefer to actually take things and differentiate everything. And it turns out that it's not terribly difficult to just force through the derivatives and confirm that the equations that we had on the previous slides are actually correct. So what we're going to do now is we're going to forget backpropagation, and we're just going to take the output and try to do a derivative of the output with respect to things in the middle. So really what I want is, I put in some input values, I got some output value, I know what I want, I know y star, that's the target value, so my error is just the difference between the output and the truth. So can I differentiate that error directly with respect to some edge weight u? And it turns out that it's really not that hard. So I'm going to start with simpler things, right? So let's differentiate the error with respect to one of the first units, the hi, the units in the last hidden layer. Right? The units in that layer, they compute their value as just the sigmoid of the bias for that unit plus the dot product, the weighted combination of the previous hidden layer times the weights which encode the strength of connection between the two layers. So if I take the derivative of the error with respect to hi, so I differentiate that, the square comes out, cancels the 1 over 2, I get y minus y0, so that's the difference in the output. And then by chain rule, I need to continue differentiating. So now I have the derivative of the output y with respect to hi, right? And the output y with respect to hi is really, really simple. I need to differentiate the sigmoid, right? So that's y times 1 minus y, that's the derivative of the sigmoid, times the derivative of what's inside. And the derivative of what's inside, w0 goes away. I'm differentiating with respect to one particular hi, so this sum will go away except for one element, yi, which corresponds to that hi. So that's going to be the derivative of the error with respect to the hidden unit. Okay, really, really simple. Okay. Let's go one level deeper. The derivative of the error with respect to gj. Start out the same, differentiate the y. Now I need the y with respect to gj. Y is a function of h's, so I have my sigmoid. So I'm going to get y times 1 minus y. And then I'm going to have a derivative of what's inside the sigmoid, but this time it's with respect to g. So the sum is going to stay in place. It's not going to go away. Previously it went away because I was differentiating with respect to one element of the sum. This time the sum is going to stay in place, and I'm going to have the wi times the derivative of the ith hidden unit with respect to the value of the g's hidden unit. And hi, again, is just the sigmoid of a weighted sum plus the bias. So you have hi times 1 minus hi, vij, so that's the weight of the connection. I'm differentiating with respect to gj. Okay, pretty simple. And you can take that as many layers deep as you want, and it'll just look like a nested structure of a summation, and then a weight, and then sigmoid times 1 minus the sigmoid, and another summation, and a weight, and a sigmoid times 1 minus the sigmoid. You can nest them as much as you want. And if you do, one nice thing that you will observe is the sums are, the derivatives, they nest inside each other. So you can express the derivative of a deeper layer with respect to the derivative of the shallower layer. So in this case, for example, I note that that part of the summation is the same in these two things. So I can represent the derivative with respect to g in terms of derivatives with respect to h. So it's just like that. And that's the update equation that we had on the previous slide, in case you're trying to understand what backprop really does. Now, I can go one step further. If I want to differentiate the error with respect to the weight on the edge u, again, it's simple. I do the same thing until I get to u. When I get to gj, when I have to differentiate gj with respect to u, that's very simple because gj is just a sigmoid, so I'm going to get g times 1 minus g, and u times fk, so I'm going to get 1 k in there. Just that. Okay. And again, you can take this derivative and re-represent it in terms of the derivative of the error with respect to g, and if you do that, You get that equation. And these two equations are exactly what you had on the last slide for the backprop algorithm. So this is basically the proof that backprop does what it's supposed to do, that it's actually really optimizing the error with respect to all of the parameters.